It's very nice to be here again, and I'm going to try to present a few results on the activities that we're doing in Bergen that are relevant to this workshop. And you can see there's quite a list of important collaborators on this project that I would like to, on this talk that I would like to acknowledge. And I'd like to start by this figure. Sort of, it was Jerry's comment at the beginning of the meeting that where he said, you know, how did the work go? And I was here in 2008, and I talked about these things, and I remember being heavily criticized for this part of this paper. So this paper was mainly focusing on the North Atlantic, but we thought it important enough to state that, you know, initialized predictions could give you a different response for the global mean temperature, right? And that's essentially all we wanted to say with this figure. But I remember we got a lot of criticism, and well, I guess that most of that is fair enough. But the other thing I wanted to point out about this is that we also had changes in the tropical Pacific, and I think these were the things that dominated these changes here. And we also mentioned that in the paper. But we had only 3 ensemble members, and we had a very crude method for initialization. So based on what we've learned in the last 10 years, I think we might have had different conclusions about the importance or relevance of this figure then. But anyway, now I want to talk about what things that we're doing now. And I think I just wanted to start with a very familiar figure that to all of us. And it was I'd like to show it because I think it's very important in the context of the recent hiatus. And this figure is an old figure because it's from a paper in 2010 where people were still not really discussing the hiatus. But what we've seen in the last 10, 20 years is something that has been reflected in a few occasions over the past century, right, from 1920 to 1940, and then from 1940 to 1960, and then the most, well, I was going to say the most recent, but there was a warming trend here from 1960 to around mid-90s. And in this work, we tried to show, and we showed the patterns from the CMIP model and the patterns from the observations, and there was trying to suggest that actually internal variability was probably important for all of these shifts. So I think it's very important to go back to the historic record as much as we can to understand both variability and predictability of the climate system and not to overlook these things. So much of the talk is going to focus on trying to look for methods in which we can go back and to study more of the climate system. So I said that. So there's 3 things that I think that we're trying to contribute in this respect. We're doing a historic reanalysis using only sea surface temperature anomalies, because sea surface temperature anomalies are a relatively homogeneous data set, and so they provide a potential, you know, to do data assimilation back to 1900 or even perhaps earlier. So I think that this sort of method can be used for both studying the variability of the last century, but also for looking at predictability. Then we have some work that addresses, it's more for the most recent changes and looking at the role of SST and sea ice in understanding, you know, whether, for example, the Northern Hemisphere winter cooling was driven by sea ice, which is a question that is relevant, I believe, to a hiatus discussion. And the last part is, so we started work on pacemaker experiments. I've done a lot of work with this SST restoring, and we also looked at salinity restoring and things like Rim was suggesting before. But I think there are other ways to do this, and I'm very enthusiastic about wind-driven partial coupled experiments. And I want to show you some preliminary results on this that are both show some promise, but also indicate, you know, problems of model systematic error. So again, I think this approach is problematic. But I think it's interesting and worth pursuing. So first, let me tell you a little bit about our activity with the development of a Norwegian decadal prediction system and our data assimilation. So here is the Norwegian Earth system model. So that's the component of the Norwegian climate prediction system. It's based on the NCAS or the CESM, so the Community Climate Model. The main differences here are the ocean. So we use a MICOM for the ocean, which is an isopycnal model. And we have differences in atmospheric chemistry. So I think we use these are implemented by the team in Oslo. So yeah, having an isopycnal model has definitely benefits, and disadvantages as well. But it also makes it quite difficult to do the data assimilation. So that has been a bit of a challenge for us. But we think we have overcome most of these issues now. So we use, for data assimilation, the ensemble Kalman filter, which is a sequential Monte Carlo method. So you use the ensemble spread of the forecasts, or the analysis step, right, to look at the covariance. And in this case, for sea surface temperature anomaly, we use the covariance of the spread to relate the sea surface temperature to temperature and salinity of the whole column, right? So then we can get updates at fixed intervals in time, right, of the whole water column based on the observed SST anomaly in an optimal sense, matching uncertainties in the observations and in the matching uncertainties in the observations and the data and the model itself. So we started this, and this is something that is published already. To test the system, we did perfect predictability and perfect assimilation experiments. So we took essentially 100 years from a control run, and we assimilated it into another 100 years, and we did it in a 10-year repeat cycle. So that's why on this figure you see 10-year periods here, and then we did forecasts. One of the reasons we did these repeat cycles is because at that stage we had still quite some drift in our system, which was related to the isopycnal, to using an isopycnal model. But this has been, there's a reference here, so we've sorted out this problem, and now we can do much longer assimilation cycles. But this figure shows you that, I just wanted to point out that this was since it was testing, it was a very coarse model. So it was a 4-degree model, both ocean and atmosphere. And here's an index for the subpolar gyre strength, and you can see that the blue is our predictions of the SST assimilation. So the first point on these is actually the analysis, and you can compare that to the black line, which is what we're trying to assimilate into the model. The red line are perfect predictions in which we only perturb the atmospheric. We had perfect initial conditions of the ocean and perturbed only the atmosphere slightly. So I hope you can see that, at least for this index in the North Atlantic, the subpolar gyre, we're able to capture some of the low frequency variations. You can see the offset that I mentioned because we have this drift and we have a short assimilation cycle. So there's some predictability in initializing the low frequency part. We don't get some of these high frequency variations very well, obviously. And we also looked at the Atlantic Meridional Returning Circulation Index, for example, and we were able to reconstruct that on the sort of decadal timescales reasonably well. So that gives us some confidence to go a little bit further and use the approach for the real world. And so in the real world context, our first test has been to assimilate observed Hadley SST data from the Hadley SST2, because this data set actually gives you some estimate of uncertainty. The reconstruction has some parameters which are perturbed, and so you can get 100 members of different realizations of SST that were possible. So we use this information for the observational uncertainty. We're considering the period 1980 till 2005, and we use the previous version of the noise assembly which was used in the CMIP5. So this has now approximately 2-degree resolution in the atmosphere and around 1 degree in the ocean. And apart from the analysis, we've done 4 test prediction experiments. Yeah, so I more or less said this, so I just wanted to point, this is the global SST from this product, and you can see the uncertainty here, particularly as you go back to the earlier period. So just a few slides on these experiments, focusing on the North Atlantic sector. So the red line here is our analysis. The shading on these is the 25 and 75% quartile of our 30-member ensemble of the analysis. The black line here is an observed index of the subpolar gyre changes. So you can see the strong weakening that was observed in the subpolar gyre in the mid-90s. And the blue line is our free run, or our unconstrained system. So you can see that the data assimilation using only SST anomalies is able to strongly constrain the subpolar gyre index. So that we think was quite promising, and we did a set of prediction experiments, and that was the first one here starting in 85. Then I'll just skip through these. So that was 85. Then there was one closer to the subpolar gyre shift, and then there was one sort of in the mid of it was at 95, I believe, so just around the time of the shift, and then there was one after. So I think it's not so clear to what, and there's only four cases, right? So there's a little bit of evidence, I would say, that the first 5 years of the system seems to have some predictability, And you can see at the end, for example, we also stay in the warm phase. We don't go back straight to the analysis. To convince you of that, I just want to show you the upper ocean temperature anomalies this is from the EN4 analysis. This is from the SST analysis, and it's a heat content or temperature over the subpolar gyre region. And so just comparing the analysis in the EN4, and this is starting in 1980, going till 2005, you can see in the upper, I hope you can see that in the upper 2,000 meters or so, these two have a relatively similar structure, right? The bottom is the free run, which you don't expect too much structure, but it shows you the forced signal. And our prediction here, starting in 95, right, you can see at least this sort of a negative, and then the warming structure afterwards in the upper 2,000 meters was captured, but actually much weaker than observed. So we have to look a little bit more into these runs to see if some of those of our 30 ensemble members produced a much more realistic change, because we expect some of those changes to be due to the atmospheric circulation. So the strong shift in the NEO, for example. Right, so that's where we are. So we believe we have the potential now to go back to, say, 1900 and do a long-term analysis and then do some more forecasts. We still need to do a bit more verification, and as part of this testing, we're doing another set from 1950 till present. And we're going to compare not only in the North Atlantic sector, but across the globe to see how well this reconstruction method works. Now, I just want to move on to another topic. I'm not as ambitious as Doug, so I only have 3 topics. But I seem to be talking rather fast. I hope people are following me, so stop me if it's not the case. I just want to present some work in which we are trying to understand whether SST and sea ice were responsible for some of the most recent changes over the Northern Hemisphere. And this is a preliminary work in the context of a Nordic project. So we have several Nordic countries involved. So we have actually a multi-model set, as you will see, of experiments to test the robustness of this result. And I just wanted to, so there wasn't too much discussion of this, of the spatial patterns over the Northern Hemisphere winter in this meeting. So I just wanted to emphasize this a little bit. And this is some work from Cohen in 2012, and it shows trends. It's not quite the hiatus period, it actually goes back earlier. It goes back from 1988 till 2010. So it's a much longer period to compute a trend over. So that is the full trend at the top, right, for that period of time. And you see during this period of time, there's actually a strong cooling. So that this is a 2.5 degrees or so, a cooling trend over this period of roughly 2.5 degrees. I think that's for the whole, it's not a trend per, I think it's for the whole time. So this 20 years or so. The bottom, and the main point for showing this, well, first is that the hiatus is expressed strongly in Northern Hemisphere winter, Eurasian climate. The second point to mention that is that that I wanted to mention is if you remove the Arctic oscillation effect linearly, right, then actually most of this trend is removed. So to me it seems self-evident that most of the changes over land, right, are dynamically driven by dynamical circulation changes. So if you want to predict this part of the hiatus change, you have to be able to predict Arctic oscillation changes, which is a challenge. So to try to understand whether that is possible, we have done sets of experiments following a methodology from James Screen in a paper from 2013. And we take AGCMs, right? We drive them only with SST and sea ice changes. And then we do 2 sets, and here we're considering the period 82 to 2013, in which we have a relatively high resolution SST and sea ice data. So we use 1/4 degree data from NOAA, and this is daily resolution. We use CMIP5 for external forcing, and we have 20 members. This is our aim, to have 20 member ensembles for all experiments. And we do 2 different types of experiments. We do an experiment in which we have observed variations in both SST and sea ice for the whole period. And then we do a second experiment in which we set the SST to its daily climatology. So we can see whether the impact of sea ice changes only. So this is just a table to show that we have now 7 models involved in this activity. The first 5 are actually involved through the project, but and 2 are sort of later editions from interested parties. So I just wanted to point out that more welcome. And this is the sort of our status. So we have this actually should be updated. They've completed now their set. So we've done some preliminary tests. So we found some errors in our forcing, and we're in one particular year or so, and then we're redoing these experiments again. But nevertheless, there's been some consistency in the results from these different models, and I just wanted to show you the trends here. This is from 82 till 2013. The scale here is degrees Celsius per decade on the bottom. The era interim trend, and here you see Northern Hemisphere. So you see the Arctic here, and you see the warming in autumn over the Arctic on the Russian Eurasian side. And you see changes over land, warming over land as well. In the SST, in the full experiments, right, you see they generally tend to reproduce that structure quite well. This is from the CAM4, and this is from the ECMWF IFS system. So that's sort of promising. Winter is quite different actually in our experiments. So I was interested to see Doug's results the other day. That's sort of in strong contrast to this. So we're not able to reproduce the Arctic amplification in winter. So you see that the strong warming over the Arctic in the observations. You see the cooling that I pointed out from the Cohen paper there over Eurasia in winter. Now the model responses, they don't capture the cooling definitely over Eurasia, and the warming over the Arctic is very subdued. Right? So you see the changes, the warming structures here in the Arctic in the models basically could reflect where the sea ice has shifted. Right? So the missing sea ice. But the large-scale structures are not present, and if we remove the SST variability and we set it to climatology, we more or less get essentially the same structures that you saw in the top figure. So this is still preliminary work. It shows some consistency between the two models. So I can think of two explanations for why we're not able to capture this wintertime cooling. Could be that both of these models have some inconsistencies in their experimental design, so they're not able to realistically capture, those sea ice changes. The other could be that actually the winter changes have a strong dynamical atmospheric component, so internal atmospheric dynamics. So we're looking into this a little bit further. Now, I don't have too many on this. So I'd like, this is a bit more preliminary stage. So I just wanted to introduce this wind pacemaker experiments. So what we do in these experiments, and our model here is the Norwegian Earth System model. We're going to run with 6 ensemble members, and we have a control experiment, which is our historic run, so with external forcing, unconstrained. And we do a second run, or a second set of experiments, in which before the ocean sees the model winds and the model fluxes, we write over the model wind momentum flux. Right? So the ocean sees the observed, well not observed, but from the 20th century historical simulations, from the 20th century historical analysis, from COMPO, we write over the anomalies, all right, in wind. So the ocean sees the anomalous changes in wind only in momentum. Our motivation for this is actually that we believe it represents thermodynamic coupling better. This was something that Christopher alluded to before in the AMIP type experiments. So that was our main motivation, and because we were interested in the connection between AMV and the Indian summer monsoon, and these effects are much more important in the monsoon regions, we thought this was important. So this is now just three slides or so that show you quickly what we found from this approach. So this is just a direct comparison between the simulated SST in those experiments and the observed SST over the whole period with detrended data. This is for the monthly anomalies. So as you would probably expect, you have strong signals in the tropical Pacific, the ENSO signal, but there are regions in other parts of the globe that momentum forcing seems to be of relevance for SST variability. Now, if you just consider the decadal timescales, so this is 11-year filtered data, which is actually of more interest to us, where actually the regions in which we're able to constrain the system are much less. We seem to have some ability in the tropics, perhaps as I will show in the North Atlantic sector. So this is just the global temperature changes in our simulations. Red is this momentum partial coupled runs. Black is the observations, and blue is our historic run. So actually the historic run is able to capture the low frequency changes in the observations relatively well on this time scale. So and the amplitude is quite similar. When we put in those observed, or the NOAA reanalysis momentum flux, we actually overestimate those changes. I would argue we get the phases better, but the scale, you can see by the size of the anomalies that they are much stronger than the observed global changes. The top figure shows you the same thing, but for the Atlantic multi-decadal variability index, so North Atlantic average SSTs, and the bottom figure is for NINU 3 SST averaged. If you just looked at the top one, you will see that the red and the black, so our momentum fluxed run and the observations seem to agree in this index up to around maybe the 1950s or so, and thereafter we're not able to phase the AMV with this momentum flux only. And this, from further analysis, we see that this is really due to changes in the subpolar gyre, which is interesting. And you can see in the bottom one that the AMV, the NINU 3 SST index is a very strongly overestimated, particularly in the mid-century, which I think to a certain extent actually calls into question the consistency of the SST and the wind products in this NOAA reanalysis. The last figure to show is the Arctic amplification in our model. So the red is from the tau force run. So, well, the black is from the HAD crew data and actually doesn't seem to reproduce, or doesn't have a very strong Arctic amplification in the mid-century. Well, it's of similar strength to that, so it's probably not too bad. The blue is our historic run. It has it there, but it's a little bit too strong, I guess. And then the red one really overestimates this. But it's interesting that the early century warming or mid-century warming can be captured in the Arctic only from momentum forcing. Right, so just to wrap up, I think we have some promising initial results from a couple data assimilation of only SST that will give us the potential to consider the whole of the historic record for studying variability and predictability. So I think is relevant here. We've been doing some experiments to understand the impact of SST and sea ice changes, so more from a mechanistic perspective, and for the most recent period, using a multi-model set. And this is showing some interesting results, as I showed. More work is needed there. And then we have this wind partial coupled model experiments. They seem to capture some aspects of past variability, but yeah, it's not perfect. So let me just finish there. Thank you.
Just a short comment. I mean, it looks like if we use your methodology for using only SSTs in order to simulate it could help the pacemaker idea.
Yeah, I think for us, if we're going to do this, I would like to do only the data assimilation in the North Atlantic sector.
Right.
Yeah.
And so you take the AMV SSTs and
you can correct both temperature and salinity in the whole of the vertical.
There you go.
But I'm not sure that's why I was asking a bit about the objectives yesterday. What is our real objective? Yeah.
Back to 1900. You've shown that it works quite well for the SST, for instance. If you looked also at water mass properties, for instance, the Labrador Sea, how do they look like in the past compared to today?
So we've only had the runs from 1980 to present, and we haven't looked. What you've seen is more or less all we've looked at, and we've only looked in the North Atlantic sector too. Yeah. So at least there's some support for more of the ocean is constrained by when I showed the temperature profile of the whole of the subpolar gyre. So the subsurface is also corrected.
Was it something that really ought to do some similar kind of experiments in the very past? You have this slowdown of the MOC, for instance, and then recovers of the 1920s. So would be worth to look at whether
yes, I agree. Yeah.
Solve this.
On the sea ice part of your talk, you kind of the way I read you. Is you were suggesting that there ought to be a connection between sea ice loss and Eurasian cooling in winter. I'd just like to point out, we have a new piece submitted. These are very, very long time slice experiments. And it's clear from those experiments that there isn't a connection between sea ice loss and Eurasian cooling. It can happen by chance occasionally in these experiments, and it typically is associated with a circulation response over the Barents Sea that's conducive to an advection of cold air over Eurasia, but it's something that you wouldn't ever see in these kinds of experiments, and it's just simply an example of an extreme episode of the very good.
I'd just like to, I think the motivation for the project that funds these experiments was to try to understand whether that is the case or not, because I tended to have a negative, I was more in the negative camp than the positive camp. So.
But it's interesting that some people find that there is a response.
Yes, I agree.
This can be resolved in the experiments that we produce.
Yeah.
They're just simply, it's another sampling issue.
I mean, we find from the observation record, there are indications that say November sea ice changes in the Barents Sea can lead to these changes. So there are some indications, but on intra-annual timescales, not the trend I'm talking about. But
yeah, just a comment with your last number 3, driven partial coupled experiments. You are using the contour 20th century reanalysis product. Did you actually just use it as it is without any additional massaging?
no, we didn't massage it at all. Yeah.
So you just use it as it is?
Yes. Is that a problem?
Yes.
But we only change momentum, right?
Yeah, but
Different.
Okay, before Doug asks his question, Matt, why don't you come up and start the translation?
So just on your third point there, you kind of mentioned this could be an alternative methodology to Pacemaker and fun, but it seems that you didn't manage to
Explain the AMV, especially up to the 1960s. How would we do that using the wind data? What would we do?
Yeah, I think that it wasn't as promising as I thought, this approach. And then in hindsight, I recognise that's not surprising because buoyancy forcing and heat fluxes is important for it's been shown to be important since the 1950s. So I think another way is perhaps to introduce something like a West type feedback, which could change and then but still leave coupling more consistent.